Hello, John Levesque again. What I'm going to do in this video is look at the perftools-lite data and investigate the application using that information. Alright, as before, I'm going to use two windows. In the top window, I am going to look at the call tree that we generated in the last video. Alright, and what this is saying is that sweep Z uses most of the time. Now, 38.6% of that time is spent in outside of these loops. And that is primarily the MPI all-to-alls, which are not displayed here. And so what I want to do is look at sweep z.lst. Remember, the LST file was obtained by using the -h list equal a. So we're going to go forward here. And we can see the looping structure. First off, we have a quadruply nested loop that is actually packing the buffer. And that buffer is being used in the MPI all-to-all. Alright, then after that, we come down and we have a J loop and an I loop. And then the K loops are all on the inside in this Z sweep. And so you notice some of these are vectorized, others are not. And notice that this is not vectorized primarily because there's tremendous striding. So striding through an array is actually better done in scalar mode unless you have some good hardware gather scatter. And so notice that N does stride by KS, which is a relatively big stride. And then this is striding on K on the third subscript. So this is not a very good, very memory bandwidth limited. As we saw in the very first video where this application is very memory bandwidth limited. Now in this next loop, it does vectorize. But here we have call ppmlr. And now below ppmlr we see it calls reman, remap, and remap calls parabola. And this is how much time is spent in remap exclusive of the call to parabola. Paraset, volume, and then ppmlr then calls parabola. As a matter of fact, let's look at ppmlr. Okay, as you can see, calls boundary, it calls flatten, it calls paraset, it calls parabola 3 times, it calls states, Riemann, evolve. Now whenever you see a D, that basically is not executed. And The reason it's not executed is because the compiler knows that this is not true. And so not only does it since xwag is only used in here, then it doesn't even calculate that. And then it calls remap. All right. So let's go back to ZSweep. So we can see that there is a fairly significant call tree below ppmlr. Then we have packing of a send buffer. Here again, this is not vectorized. It's unrolled by 8, primarily because of the striding. And then we have a call to MPI all-to-all. And then we have another copy the receive array to the send array. And here again, this capital R means that these are rolled into one statement, these 6 statements, and then it's vectorized on the very first subscript. That's what that capital R means if we go back to our legend. Re-rolling. So the compiler really does some pretty significant stuff. Now, let's talk a little about what would it take to thread this loop. We probably want to thread it on J. I think I is 32, I'm quite certain. J is 64 and K is 64. So what we have to make sure is that all of the variables that are set and then used are always set before being used. Something that's a little more difficult is when you have an array that is not referenced on J. Like all of these arrays are independent of J. So each iteration of J, there's a whole array that is generated here. And then R is used down below. So the question here is, are all the values of R set before being used? If they are not, then you have a loop carried dependency. If you investigate the indexing here, you will see that indeed all of the elements of R are set here before being used. But it gets even more complicated because down the call chain, these arrays are all used. As a matter of fact, it gets worse. Let's look at one of these modules. Notice that R, P, E, Q, all of these arrays are in a module. Now, if they are in fact independent of J, they need to be private. And if they're in a module, they can't be private. So one needs to either take them out of a module or use the OpenMP thread private directive to make all of these private. So as we can see, there are definite issues here if one wants to use OpenMP on this loop. Now I have done this and it does help a great deal on performance-wise, and it is. All of these outer loops on these suite routines are in fact parallel and can be parallelized. Okay, so that's it for this video. Thank you for your attention.